Not so far ago in time was that we realized that our universe is expanding, that our universe had started off from a dense compact state to now in an expanding state. But just about 2 decades ago, we found out that the universe is not only expanding but is accelerating expanding. And that was a bigger mind blown in the physics community than the former. We are talking about the mysterious force pushing our universe apart, dark energy. So it was 1929 when Edwin Hubble discovered that our universe is expanding and that everything in the larger scale of the universe is moving away from every other thing. This discovery led to the idea of the Big Bang. If the universe is expanding, it must have been small in the past. Go in the past enough and you get the Big Bang. The discovery of the cosmic microwave background in 1964 confirmed the Big Bang picture. So yes, our universe is expanding, and almost everyone in the physics community thought that this rate of expansion of the universe will be getting slower with time because, well, there's something called gravity in our universe which acts opposite to this expansion and brings everything together. So in an attempt to measure the rate at which the expansion rate of the universe would have been slowing down, scientists found out that the rate of expansion of the universe is actually not slowing down. On the contrary, it is speeding up. The rate of expansion of the universe is accelerating. And the thing that was supposed to cause the rate of expansion of the universe to accelerate was termed dark energy. Energy because we think that it is some sort of energy that is causing the universe to expand, and dark because we don't know what it is. Cool name though. Now, what can cause something like this to happen? What can dark energy be? The first thing that comes in mind is something that has an anti-gravity effect. In Newton's theory of gravitation, gravity is always attractive. Everything attracts every other thing. But in general relativity, that is a more refined theory of gravity, gravity can be both attractive or repulsive because in general relativity, gravity is the result of the curvature of space-time. So whether it will be attractive or repulsive depends upon the precise geometry of space or the way in which energy has been distributed in space. There is mass or energy curve space-time, and that gives us an illusion of gravity. Now in Newton's theory of gravitation, it is only mass that can cause gravity, but in general relativity, any form of energy can cause gravity, because in general relativity, mass itself is equivalent to energy by E equals mc square. Now since positive energy causes attractive gravity, the first thing that comes in mind for something that can cause repulsive gravity is obviously negative energy. And quantum mechanics allows for negative energies. In quantum mechanics, the vacuum of space is filled with energies popping in and out of existence that can randomly take up a negative value. But this is not enough. So, is negative energy the only thing that can cause repulsive gravity? Well, not really. There are other ways. Because you don't really need negative energy to get repulsive gravity. As said, in general relativity, any form of energy can cause gravity. That includes mass, momentum, pressure. And this pressure is what that can give us repulsive gravity and an accelerating, expanding universe. Positive pressure pulls outwards, like a compressed gas in a cylinder. It is when the system has more pressure than the environment surrounding it. And negative pressure pulls inward, like a stressed spring. So it seems like what we need for an expanding universe is positive pressure. But no, because it's not the pressure which drives the expansion of the universe, it's the gravity because of it. And repulsive gravity is when we have negative pressure and not positive pressure. And what can give us negative pressure? Well, it turns out that if there is a region of space filled with constant energy density, then it will give rise to a negative pressure, which will in turn give us repulsive gravity, which will in turn drive the accelerating expansion of the universe. And this is the most famous hypothesis about what dark energy can be. It is the energy inherent to the vacuum of space. The energy inherent to space creates a negative pressure which drives the accelerating expansion of space. Again, since the energy density is constant, pressure isn't gonna do any work. The first time the idea of vacuum energy started was with Einstein. Einstein believed the universe is static, but the equations of general relativity predicted that a static universe will not be stable. It will be either expanding or contracting. This is when Einstein came up with the cosmological constant, the energy inherent to the vacuum of space that will yield repulsive gravity and will counteract the force of gravity and was supposed to make the universe static. But later Hubble found out that the universe is expanding, and the need of cosmological constant vanished, and everyone forgot about it. Until it turned out that the expansion rate of the universe is not slowing down, rather it is increasing. And this is when the idea of cosmological constant revived. So, according to this view, our universe is filled with an unknown form of energy that is inherent to the vacuum of space, and that this is causing the universe to expand at an accelerating rate. We call it the cosmological constant. A very similar idea was proposed by Alan Guth and others that expands the early universe exponentially. Quickly after the Big Bang, there was a phase in the universe in which the universe expanded exponentially. We call it the inflation, and it is believed that this was the result of an energy field having a positive non-zero value, just like the vacuum energy we talked about. It is called the inflaton field. Now, since we've talked about the vacuum energy, cosmological constant, and how it can be a candidate for dark energy, there is a subtle thing about dark energy that I want to point out. The universe was not always accelerating expanding. It only started to expand at an accelerating rate about 6 billion years ago. And before that, the expansion rate of the universe was slowing down. So where was dark energy back then? Why wasn't it causing the rate of expansion of the universe to accelerate back then? Well, the answer is hidden in the details. Dark energy is the energy inherent to the vacuum of space. After the Big Bang, the expansion rate of the universe started to slow down because of gravity. Why? Because there wasn't enough dark energy back then to counteract the force of gravity. But as the universe expanded, the amount of matter started to get diluted in space. Plus, since dark energy is the energy inherent to the vacuum of space, as the universe expanded, the amount of dark energy in the universe increased. Because unlike ordinary matter, dark energy does not get diluted in space. Rather, the more the universe expands, the more dark energy there is, which makes the universe expand even more, which creates more dark energy, and you got it. So till about 6 billion years ago, the force of gravity was strong enough to hold everything together. But after that, dark energy took command and made the universe expand faster and faster. The amount of dark energy in the universe increases as the universe expands. From where does that energy come from? Nowhere. Doesn't that violate the law of conservation of energy? In short, it does. But it's not a problem because, well, in general relativity, energy doesn't have to be conserved. I'll talk about it in a bit more detail in an upcoming episode. But till then, tell me in the comments, what do you think about it? Our observation tells us that for everything to work out nicely, 68% of the universe should be dark energy. We can't, however, use this 68% of the energy of the universe for any practical purposes because, well, it's constant everywhere, so it doesn't matter how much there is, we won't be able to use it. Now, cosmological constant is not the only thing that dark energy can be. After all, we don't really know what dark energy really is. Another famous idea is the quintessence. It demands for the existence of a scalar field permeating the entirety of space. It is different to the cosmological constant in that it can change with time, whereas cosmological constant remains constant every time, everywhere. And it is similar to the fields that exist in the quantum field theories. According to quantum field theories, particles are just excitations of quantum fields. For example, electron would be an excitation of the electron field, and in a similar way, every other particle has its own corresponding field. Now, in quantum field theories and particle physics, there are particles called bosons which are scalars. Quintessence is also a scalar field, so the corresponding particle of the quintessence field would also be a scalar particle or a boson. And since bosons transmit forces between matter in particle physics, quintessence, if it truly exists, could be the fifth force of nature. There are also other modified gravity theories that eliminate the entire need of dark energy or dark matter by changing the way gravity works, but they possess many other problems. Currently, it seems to be the case that dark energy really do exist. Now, even though it all might seem like we know a lot about what dark energy is, the truth is we really don't know what it is. What we know is that there is something that is causing the universe to expand at an accelerating rate. What is it? Well, we have some theories about that, and it might be the case that they are true and it really is what dark energy is, but we really have no evidence for that. The most famous hypothesis for what dark energy can be still is the cosmological constant. No proof, however, for any of it.